one of them. Okay? And also, I kind of abused everywhere. I didn't point out everything from the point of view, which is Gaussian processes, which is another big class of stochastic processes that can be used in a lot of modeling problems. And there is a beautiful connection with ideas in integral equation, which is completely invisible here, sampling theorem, inverse problems. I didn't do it just because, again, I'm trying just to give you algorithms and the way to use them, okay? And I just want to try to stay away from too much math and theory. Other stuff that I didn't tell you at all is a lot, which is actually more important, what I'm trying to achieve today, is a lot of different kind of generalization of this. For example, square laws. Why square laws? Something else? Sure, go on. You take so-called logistical function, you get logistic regression and kernel logistic regression. You take so-called hinge loss or epsilon sensitivity loss, you get supervector machines. All of this will be kind of, once you know this, then you just have to add a little bit, and you know all these other algorithms, okay? Another thing you could do is to say, why binary labels or real valued functions? Can I learn vector valued function? Sure. It's much harder. You don't have a very good idea of how to build function spaces, but you can do that, okay? And I didn't tell you how, but you can use to multi-output function, and for example, to go from binary classification to multi-category classification. And it's going to be a minor twist, again, at least the basic solution will be a minor twist over the solution I just told you now. From a practical perspective, the thing you should remember is basically that now what you can do is you can build your own dictionary, but you can also use these kernels that do give you a bunch of different solutions. So, what is this? No? So let's close it. Let me just start 1 second. Oh wow, you draw a lot of stuff. Oh, so this is linear, grain, this. Okay. Now let's see what happens if I switch from this to the Gaussian kernel. This game I'm playing is kind of the one game that all of machine learning people spend most of their time doing. They have a problem, they build this kind of algorithm, they take the linear kernel first, kind of not so good, but in high dimensions they might do well. But let's try the Gaussian kernel and let's play a bit with the sigma. This is what's going on, this is exactly what I'm doing. So let's try. Take the Gaussian kernel, I take the regularization parameter, this is the lambda, this is the sigma width. Train it, doesn't break, so happy. Test, and pretty cool. Okay. Of course, all these parameters that I'm throwing there, I could do and I should do a cross-validation. Okay, this is just to show you what you get. This is kind of the general idea. This is what you get with these squares, with linear kernel, and this is what you get with the Gaussian kernel. How you should think about this? Remember, this is not f of x. This is f of x equals 0. How does f of x look like? It looks like this. Sit on here and put a Gaussian of width 0.04, whatever I chose. Okay? And do it on every single point. Then you have to choose the height of the Gaussian and the sign. If it's positive, it comes out. If it's negative, it goes up. Then you connect all the tip of these mountains, and you get something up here and something down there. Okay? Then you look at the levels at 0, and this is what you get. And this, I was lucky, and it looks like I chose some sigma, which is kind of reasonable. Let's see what happens if I try to make it much smaller. Nothing. Big break. I'm really going a bit random here because I don't know what is the numerical person. I didn't look at the eigenvalues. I don't know what's going on. Okay, so I just changed sigma. Okay, and I make it very small, but very small because I get, there is a Gaussian here. Okay, and basically I can get to stuff like this. And what you see is that you start to see that this is really probably a mountain and a valley, and it goes up again. And for some reason, it wants to go up here again. Okay, so this is really something going up and down. I wanted to try to show to you that if I try to make this smaller, let's try this. Okay. So what I want to show to you is that if you start to play around a bit, and if you play with sigma, what you can do is basically really put a bunch of Gaussians. I didn't prepare any setting. I'm just playing live on this. But you could literally go and start to look at this solution. This is really clear. There is one Gaussian here, one Gaussian here, and one Gaussian here, pretty much. Okay. And so you can circle out points. Okay. These are small. They don't see each other. These start to behave very similar to a local method. Okay. You basically just put the Gaussian around each point. And so you get, by using the Gaussian kernel, you can get this whole range of complexity. Does it make sense? If you go on the other side, and you put here, let's try one. So if you go on the other side, so if you do regularize, and you just be, but the point I want to make, to show it to you, is that the more you make the Gaussian big and the more you regularize, the more, this is exactly the same data set as before, but if I can keep on going, in the end, this is going to behave essentially like the linear kernel. I make Gaussian so big that essentially I'm going to have a function which is very smooth, okay? Now, these algorithms are really the workhorse of most of applications, okay? Might not be least squares, might be super vector machines, might be logistic regression, but this is what's going on, okay? A lot of state-of-the-art solutions for supervised learning are based on these methods, okay? Either for intelligent system or just make prediction of all kinds of practical problems. And we worked for like an hour on this, and we learned that we can play around and we can switch from one complexity to another complexity. And by essentially using the same code and just changing the per processing, choosing different dictionaries or choosing different kernels, we can actually get a whole range of different kind of models, going from linear to something more complicated. And so we actually can start to ask, what else do we need, okay, to solve supervised learning problems? It's a pretty big toolkit box already. But before asking what else we need, I think it's good to take a break. We die. Think of what else you want to see.